Let's talk about elastic potential energy. We'll start with something we're familiar with. What if I wanted to lift this block up? I'll have to apply a force through a height. The minimum force I have to apply would be equal to the weight. What happens to the work that I do? The positive work that I do is taken away from this system by gravity. It does negative work, but that doesn't mean this work is gone. It's being stored as potential energy, gravitational potential energy. The block has the potential to fall back down. Let's make a graph of the force that I apply through the distance h. My force is going to be constant, so I get a horizontal line. What's the meaning of the area under that line? It's a force times a distance. The area is the work that I did. It's also going to be equal to the work taken away by gravity and stored as potential energy. Remember, we're assuming we're only pulling as hard as we have to fight gravity, nothing extra. Let's assume the object weighs 10 newtons and I raise it 5 meters. Gravity has stored 50 joules of energy. Well, let's compare this situation to compressing a spring. I have to apply a force to compress the spring. And as I compress it, the spring pushes back on me. As I compress the spring, I have to push harder and harder because the spring pushes back harder and harder. Well, let's make a graph of the force I'm applying versus the distance I'm compressing the spring. We'll call this distance x. What do you think that graph is going to look like? Give it a thought before I draw it. Before I compress the spring, I have no distance of compression. Then I'm at 0, 0. As this compression increases, I'm going to have to push harder and harder. Well, we've seen this before. We did a lab when we were hanging weights from springs. The slope of this graph is the stiffness. We represent the slope with the letter K. It's the change in force over the change in the distance. Since we start at 0, 0, we can simply say it's F over F. So what does the area under this line represent? It's a force times a distance. That's going to be work. So what happens to the work that I do compressing the spring? When I get done compressing and I let go, what will the spring do? Yeah, it's going to shoot back out. The work that I did to the spring is going to be stored in the spring as potential energy. We say the spring has the potential to shoot back out. So this area is going to be the potential energy elastic, whereas this is the potential energy gravitational. So how do we calculate this area? Could you just take, say, 10 newtons times 5 meters, like we did at this graph? Well, the area is a triangle. So you're going to have to put a 1/2 out in front of the force times the distance of compression. So we'll have 1/2, 10 newtons times 5 meters, which is 25 joules. But what if we didn't know the force, but we just knew how far we compressed it? Well, there's one more thing we can do. We can use K, the stiffness or the slope, and replace F. If we say F equals K times X, and we put it in here, we get 1/2 kx squared. And that's the formula for elastic potential energy for a linear spring. Let's check it out with the numbers. We have 10 newtons over 5 meters for the slope of this line. That means K is 2 newtons per meter. We take 1/2, 2 newtons per meter times 5 meters squared, and we get 25 joules again. So now remember, gravitational potential energy is mgh. Elastic potential energy is 1/2 kx squared, where x is the distance of compression. Well, let's say we have a spring with a constant of 200 newtons per meter, and I have a cart, frictionless, 4 kilograms. I'm going to start from 0. I'm going to compress the spring 30 centimeters and then release it from rest. What's going to be the velocity of the cart when the spring has pushed back to its original length? Yep, it's conservation of energy. Well, if this is the initial position, we have elastic potential energy. We don't have any kinetic energy because we're releasing it from rest. When it shoots out to the equilibrium position, we have no more compression, so we have no potential energy elastic, but we do have kinetic energy final. So we have 1/2 kx squared, which is 1/2 200 newtons per meter times 0.3 meters squared, which is 9 joules. Now you might wonder why we didn't plug in negative 0.3 meters here. We could have, it wouldn't have mattered. It's still x squared, so it's going to be a positive energy stored in the spring. Turns out it doesn't matter if you compress a spring or expand the spring, you still have an increased potential energy either way. And now we can solve for the final velocity. And we get 2.12 meters per second. Well, what if I wanted to find the velocity when the cart has been pushed back halfway to the equilibrium position? I'll be starting from this position. That will be the initial compression. But now if this is my final position, the spring is still compressed somewhat. So I will have a final elastic potential energy because I'll still be compressed 15 centimeters. And this will now be the final velocity at that point. So the 9 joules of elastic potential energy will now be split up. Some of it's going to go to a final potential energy, and the rest will go to the kinetic energy. The final PE is going to be 2.25 joules. So we have 6.75 joules turned into kinetic energy, which gives us a final velocity of 1.84 meters per second at this position. Now it's kind of interesting to note that we've expanded halfway, but most of the velocity is gained in the first half. We don't gain that much more in the second half. Maybe we can understand that better by looking at the graph. Remember, we set this up as compression going this way. At the full compression, we're at 30 centimeters. When we expand back to 15, what part of this area was delivered as energy to the cart? It was this part of the area. As we can see, with the greater force, we're going to deliver more energy as we expand in the first half than when we expand to the second half. There's just not that much force here, which results in a smaller area. All right, one more problem. At school, we have these cool carts, plunger carts, and we can trigger them to shoot out. There's a spring inside here. They're 500 grams. The K is something like 500 newtons per meter for that little plunger. Let's say it gets compressed 3 centimeters. I press the trigger and release it. How high up the ramp will it go? Sounds like conservation of energy. This is going to be the initial position. That's going to be the final position. And that's a height final. Well, it looks like we've got a potential energy in the initial position. What kind is it? Elastic. Before I hit the trigger, it's not moving, so I have no kinetic energy. I can actually skip all the middle stages of this problem and go to the end. Do I have a final potential energy? Sure, I went uphill. What kind is that? Gravitational. If I've reached the highest point, the velocity is 0, so I have no final kinetic energy. Okay, we have a 1/2 kx initial squared, turning into an mgh final. And we have 0.225 joules of elastic potential energy initially, turning into the same amount of gravitational potential energy at the end. Plugging in, we get 0.0459 meters, or 4.59 centimeters. Notice, do you think the angle made a difference? No, if it's a shallower angle, it'll go further along the ramp, but still reach the same final height. If it's a steeper angle, it won't go as far along the ramp, but it'll still reach the same height. Now you really should check out the chapter notes to read the section and do the problems.